So I'm going to show a couple of real simple things we can do with the Shortcroft metric. We're going to do more with it, but before we really analyze it, we need something called a killing vector. And so what I want to do is after get some simple things done, so we can just kind of see some novel features. We need to get the killing vectors. It's Wilhelm killing. It's not that the idea is hard. It's just his last name is killing. Okay. So last time we had a static, spherically symmetric vacuum solution to the Einstein equations. And we worked this out. It ended up being that the metric is this ds squared. I'm going to show this in kind of. Yeah, okay, but here. Because this minus c squared, sometimes this is going to become 1. Again, we're going to use Roger units pretty soon, where sometimes it's 1, sometimes it's 8. And you just have to figure out when it's what. So this gm c squared over r, and we gave this whole thing here a name. What did we call that? I think we call it last time, something.
The RS.
Yeah, that was capital RS, and that's the Schwarzschild radius. Dt squared. Did I mess something up? Or... Okay. 1 over 1 minus r sub s. I'll keep the same format. Here. The r squared plus r squared, you have omega squared. Okay. Now there is something called I'm not going to go through the proof because the proof. Well, okay, because we don't have time. The proof isn't necessarily hard. It's one of these standard things. You can actually prove that any static spherically vacuum solution is only this. You can never have anything else that is spherically symmetric in a vacuum solution, which doesn't have this form. So just so you know that Birkhoff, and this is what Birkhoff's theorem. Birkhoff's theorem states that any spherically symmetric vacuum solution has this. Okay, whenever, so in other words, this is unique. In other words, this is a unique solution. Okay, you may have had enough math that you know something about uniqueness. Whenever you have uniqueness, how do all those proofs go? Every uniqueness, as far as I can tell, is always the same type of animal. What is it? You assume that this isn't the case, and you go through and calculate it, and you end up showing that this basically, your unique solution, which you didn't assume was this, has to be the same thing. So it has to be unique. So uniqueness proofs almost always go the same. Now, why do I mention this? Because later on, in some homework, we will study a spherical solution, a spherical metric that has the form n squared equals minus c squared dt squared plus dr squared plus r squared plus b squared. This is a constant. Okay. D omega squared. Okay, that's spherically symmetric. Okay, so from Birkhoff's theorem, what does that state then? That can't be a a vacuum solution. So that's not going to be a vacuum solution. Now that's going to be fun looking at this problem here, because this is actually going to be the metric for a wormhole. This will actually have a wormhole. So this is the metric for I'll call it stable, meaning you can get through it. Wormhole. Probably doesn't exist, but if you had something like that, and again, the complication is going to be that it's not a vacuum solution. So the question is, what do you need to get that? And you probably need something that doesn't exist in nature, but we're not there yet. Okay. So, and we're going to get something called an embedding diagram, which is going to be a way to visualize these things. And when we do the embedding diagram for this, it's going to look like your standard picture. You could say, well, what does that mean? Well, it's the state picture you see if you look at any popular science book. We'll go through and analyze that. That's later on. So before we do anything else, I just want to show you a couple of fun things we can do with this. Some preliminary results. So before we examine specific problems, meaning the precession of the perihelion of Mercury, deflection of light, some of the other things about black holes. Okay. This metric. Let's look at two simple features. Okay. So one thing, whenever you have these metrics, one of the first things you want to do is look at basically light. So let's ask the question, how would light travel in the radio direction for this metric? In other words, what we want is, we really want the space-time diagram. In other words, draw the space-time. Okay. So we're looking at radio direction. So what does it mean? It's going to mean light going toward a black hole or toward this object or away from this object. Okay. So what can we kill immediately?
The omega?
Yeah, there is going to be no angular part here. So that means in this case here, so for radio motion, your geometric. So that goes on. And what do we know for light? For light, what do we know about ds?
0.
It's 0. So any metric, if you want to find out how light travels with that, we're going to set the ds square to 0. We're going to do the same thing with any type of when we do the Kerr metric, any type of those things. That's what we're always going to do. Okay. So if we do that, you get the 0 here, we get this term, and then this term. So what does it give us? So first of all, I'm going to rewrite this. I'm going to write this as in terms of r sub s. So this will give us 0 equals minus c squared, 1 minus r s over r, and t squared plus 1 over 1 minus r s over arbitrary square like that. And if I solve this, what does that give me? That gives me this c squared 1 minus dr here, t squared equals this. Or that. Or if I've been solved this, I'll take the square root. Get that. Okay. So what happens if R is large? So if R is much greater than M sub S, what do we get? CDT over DR equals what?
The 1 minus 0. 1.
Plus or minus 1. So we're going to plot this guy here. So if I plot the red line here, here's my CT, here's my R, here's RS. What do I get here? I get something that just looks like this. Right, here's my slope. This is your slope here. This is going to look normal. This is your normal plus or minus 45-degree. Not too surprising. Now, what happens to this though is R becomes closer and closer to R sub S.
It's very large.
Yeah, so what's going to happen here is this gets closer to R sub S here. This gets closer and closer to 1. You get 1 minus something closer to 1. It becomes small. So this is going to get larger and larger and larger. So what's happening then to my light cone? It's not like this anymore. It's starting to, it has a steeper slope. So as you get closer here, it's going to go like this. And it's going to go like this. It's going to go like this. And if you write down the R sub S value, getting really close, what is it going to be?
Straight up.
Yeah, it's going to be like this. So let's say you're up and let's say this is where you live. What would we do? And let's say let's draw the road line for mom and dad. Okay, so mom and dad are at home here. Okay, so what's the road line for mom and dad if they're at home? It's just like this. Okay. You get upset with mom and dad, so you hop in your local space, hop in their spaceship, and you're gonna drive toward our nest. I don't feel very stressed. I don't have to eat broccoli anymore. Okay, so you're gonna go like this. And at some point you're communicating with mom and dad. Okay, so what's gonna happen? Well, if you're here, you know, the signals are gonna come out here like this, and if you wait a little bit longer, they come out like this, if you wait a little bit longer, they come out like this. What are your, you know, what are your parents gonna hear? Basically, you know, they're just gonna hear normal signals like that. I mean, constantly. Now what happens when you hear them? That signal is going to be like that. Now, eventually, as that signal gets closer this way, it's going to become more like that. So that line is going to actually bend up like this. But if you're to just stay here, what's going to happen here? Well, then your signals are then going to become out more like that, something like this. Now, what happens when you get here? It's going to come out like that. Well, actually, I'm going to erase some of these guys here. If you're here, you know, these signals are going to come out more like that. And then if you get closer, let's say you get over here, and that's going to come out more like this. We're going to work out the mathematics of this in detail. But what's going to happen to your parents if you're talking to your parents? What are they going to notice?
Longer time between your.
Yeah, so let's say you're going like help here, saying help here, help here. What's going to happen? The intervals between those helps are getting longer. So you know, help, help, help. You're going to start saying things like that. Eventually, what's going to happen if you're here? what will your parents see? So as far as your parents are concerned, you're just basically stopped at the edge here. We're not gonna see anything else, you're gonna stop here. When we actually go from north to south, we're not gonna do it today, but when we work it out, what's gonna happen here is that once you go into this region here, you can see a little bit about what's going on here. If your R sub S becomes basically smaller than R sub S, what happens here?
Be negative.
This becomes negative, and what's gonna happen is that things flip. So what's gonna happen is that light cone is gonna flip like that. You know, where do you have to stay? Remember, any world line is basically doing the light cone. So what's gonna happen here is that once you actually cross this region here, this is gonna be called your event horizon. I'm gonna use that more rigorous now. Probably about the end of the week. This is your event horizon. You can't come back. Okay, there's not, if you realize, oh, wow, I really screwed up. You realize, okay, well, I'll just go with them and mom and dad will forgive me. Well, doesn't matter. You can't come back. You're stuck. Okay. Now, so as far as you're concerned, you're just going straight to the center of the black hole. Here, we haven't defined black hole. That's what would happen with you. As far as your parents are concerned, what they're going to see is they're going to see you stop right at the edge. Never mind that. Okay. So that's actually one thing we can get right away about the lesson here. And again, we're going to go through and we're going to work out the mathematics of this. But not today. The lesson here is that if you have a metric and you want to figure out how the light changes, usually look at the radial corrections, but you set your ds squared to 0, and then you can figure out how light is going to travel. Okay. First lesson. You look like you have a question.
Yeah, so the light cone is like this. Does that mean your movement is at like a speed faster?
No, you're going to always be kind of in your light cone is now like this, and you're basically confined to just moving this direction here. That's all you're stuck with. Your space and time get flipped in this space. Basically, what's happening here is when you're out here, you're okay. When you're out here, your R is greater than R sub S. This is positive, and the behaves. This is positive here. This is a negative. Everything behaves like it should be. When you're here, this from here becomes negative, so you get a negative in your DT here. And then this guy here, this becomes negative here like this. And so this kind of looks like time. And then this looks like space. And so how you interpret this gets all given.
But
okay.
So even though the angle is greater than 45 degrees, you're not actually.
Yeah, you're always going to be less than the speed of light in this frame. So this, your light would be here, but you're always going to be less than it, no matter where you're at. We'll make use of that when steal more from Alcubierre. We came up with the whole idea of a warp drum. So you're always going to be locally less than the speed of light, even though that speed of light you can locally. And that's always going to be the warp drive to travel around other galaxies or someplace distant with best. Probably doesn't work. So this we can have the metric.
Why doesn't it work?
All these things basically require exotic matter, which we haven't studied yet. And that probably doesn't exist, but it makes for good science fiction. So again, if you want to study light, what you do is you set your ds to 0, and then you can study how light is going to move in that method. So that's the first thing you want to do. Then I want to show you where just this metric kind of gets odd. So let's do a little example here. I've already alluded to the fact of, let's say here's the sun. Here's something like this. And I'm going to come out and I'm going to measure the circumference here. So this has some circumference C1. I'm going to measure the circumference here. I'll call this C2. And we're going to call the radial distances here. I'll call this R1. This would be the circumference over 2 pi. This is what I mentioned before from Wheeler. This is his suggestion. And then this one here over here, R2, we'll call this C2 over 2 pi. Because remember, we did that little calculation showing that what you call R is not unique. You can actually have different values of R. So he specifies finding the R this way. And so let's say we did this little calculation here, and let's say this distance here is 4. Let's say we did this little calculation here, let's say this distance here is 5. So the question is, what is this delta R here between the two? You look at that and say, well, it's 5, 4. So 5 minus 4 is 1. Pretty obvious. Okay, let's go through and do the metric. I'm going to see you're not going to get that answer. So let's go through and do this. And you're going to tell me how to do it. So let's ask what is delta R. Again, our metric is this. You tell me how to calculate you tell me how to calculate delta R. Oh, what's going to be T or DT? 0. Yeah, we're going to do this at a constant time. So your T is 0. So your DT is 0. You're only looking at a radio distance. So omega is 0. D omega is 0. Because we're theta and phi are constant or fixed. So d omega is 0. So what does that tell me? That tells me that this ds squared equals this guy here. What else we call those kids? With that. Okay. So what do? We take the square root of both sides here. And this tells us that the ds, which is again what we measure, is that. Okay. So what would we do? That integrate from 4 to 5. Okay, so let's put it in a slightly better form. So what might we do? You can work on all the details in homework, but I'll get you the push here so you can see it's not going to be 1. And that looks a little ugly. Make it look a little prettier. I probably multiply the top and bottom by R. Why would I do that?
Would that make a trade sub easier?
Yeah, it's going to become kind of a true sum thing. Actually, I might even do. I might do like a half in here too. If I did that, what would I do? I have the start in 1/2 power over square root of R minus R sub S. This. And then that spells trig sub E. Okay. And then you're going to solve this. And then you're going to say then your delta S is going to be your integral then of this ds here. And it's going to be this integral from basically 4 to 5 of okay, and you can see that this will definitely not be 4 minus 5. Okay. That makes sense. You're going to find actually it's greater than that value, meaning that there is more space between them because again, your space is curved. And so there's more space in it. That makes sense. We have a really nice experiment. Basically, we're actually going to do the calculation. It was done by Shapiro. Shapiro was actually a professor. Actually, there's a story in one. Let me just set this up. So we're going to do a variation on this argument. And so here's the sun. And so here's Mars. It might be Venus. I don't remember the entire thing. I think here's Earth. And what you can do is you can have a little satellite here sending a signal here. So that signal is going to go basically from Mars to Earth, and you're going to pick up the signal. Okay, so what can we do? We can assume that basically relativity is wrong. And if relativity is wrong, how long would it take for the light signal to get there? You take this distance, divided by the speed of light, and that would be the time. And you can get some value. Now, what you can do is you can assume that relativity, meaning general relativity, is right. You can then use the Shosha metric, and you can basically then calculate the dt for this, the time it takes for this light to go there. What's going to happen in that case here, because there's going to be more space in here, there's actually be a time delay. This was actually this was proposed as an experiment by Shapiro. And actually, it works actually quite. You're gonna actually look at it.
And there's a d omega too, right?
There won't be a deal because there would be a little bit of motion here, but in the grand scheme of things, it's first. So there is no I mean, as far as changing with time, there will be something you're gonna have to integrate over with the omegas. You're gonna have to figure out account for that, and I'm gonna leave you if you want to. This actually be a little vision. The reason I started with Shapiro is he was initially a professor at Cornell. And then he was actually good friends with my favorite professor at Illinois, Gordon Bing. Don't know the history of it. All I know is that he was accused of double dipping from his grades. And he was fired from Cornell. And so he needs a place to live. And so he basically, Gordon Bing got him a job at the University of Illinois. And that's how he ended up there. And at some point when he was coming, he was going to teach a course. And it was going to be basically on black holes or who knows what. There's basically this specialty. Maybe it was in general, because I don't know what the course was. Well, it's going to be what you're going to learn in the class, and then some students went by and wrote on a little flyer, you know, how to double dip from your grant and how to do this and this. And he just put all these other little comments in that might be other topics that he would include in this class. It turned out it didn't go over well. That was not appreciated. Okay. So, how can you go about solving a lot of these problems with any metric? Well, when you look at any problem that's really hard in physics, what you want to do is you want to look at basically conservation. You know, what is conserved? And I'm going to tell you what to do, and I'm going to then prove the result. So, I'll get this over here. Okay, so directly solving the metric is often difficult. And by solving the metric, what do I mean by that? I mean really setting up, basically setting up your geodesic equations. You can set up the geodesic equations. You can solve them, and you often have to, but that can be really hard. So by this, I mean, I'll be setting up the geodesic equations from the. So that's what I mean by directly solving that there. An easier method is to look for conserved quantities. Okay. Here's, I'm just gonna state this, and then we're gonna prove, the rest of the class will be proof. Okay, so we will see. We will show that if the metric tensor does not involve, does not contain x mu. And by this I mean, you know, either an x0 or an x1 or an x2 or an x3, if it doesn't contain one of those. In other words, this is 0. Okay, then d p alpha d tau equals 0. So p alpha equals a constant of motion. Okay.
What is P here?
That's, thank you. Okay, so the P is our standard P. So I should state that. Okay, so P alpha is going to be what? M times U alpha. This is M dx alpha d tau. Okay. I haven't proved any of that. Let me kind of show you an example of what I mean by this. Then I'm going to go through this. Oh, we have to set up something first. So in our case, we had this. Okay, so our G mu nu is independent of what in this case? Which is independent of. And then remember our x mu is what? Our x mu is T R
Theta and B.
theta and phi.
Depends on all of those.
Yeah. You have to look at the G's.
Oh,
It's a G.
it's just the constants in front of the DTD.
Okay, so this guy right here. This is G00. This is G11 or GRR. I can call this GTT if I wish. Now, what about G theta theta and G55 or G22, G33?
It's just consistent.
So G theta theta or G22 as well. And what does this whole thing here mean? Theta is, ooh, no, that's all. So G theta theta or G22 is
R
squared. And then G55 is what?
R squared sine squared.
R squared sine squared of theta. So what doesn't our G depend on?
T
T and phi. So G mu nu does not depend on T or phi. So we're gonna have two conservation laws. So that means that d p0 d tau is 0. So that means that p0 is a constant. Okay. What do you think that one's going to give rise to?
Yeah.
That's going to give rise to conservation of energy. Okay. And then we have dp3 d tau equaling 0. In other words, p3 equals a constant of motion. And that's going to give rise to conservation of
Angular momentum.
this would be conservation of angular momentum. Okay. Then I'll show you how this is then connected to the Killing vectors, because it turns out the Killing vector initially we looked at it seems a little cheap. Really? But we get to use Cassie again. Cassie is frequently used for the Killing vector. So everybody can see it. Okay.
I would be on time if I don't need to stuff. But it keeps crazy.
So this is going to be one of the standard things you do when you come across a metric in GR. You're going to say, oh, this doesn't depend on of these variables. This doesn't depend on these variables. Therefore, I have to have a conservation law. This is going to help us immensely. Okay. Questions for that? Good. Okay, so before we prove this, I think I probably should come on. Oh, it doesn't. It does. So before we prove this theorem, meaning that your G doesn't depend upon one of the x mu's of all the components, and depend on one of the x mu's, and you have this conservation law. We need to look at the geodesic equation. Okay. So let's kind of do a couple of funny things here. So let's look at dx mu d tau where v mu is an arbitrary number. Okay. Now, how can I write that? I can write it like this. I can say that's really the partial of v nu with respect to x mu dx mu d tau. Am I doing that? What have I done? I've just used just a channel. So that's this. Okay. Now, we're in a manifold, and what do we know about a manifold? A manifold is locally flat. So this is fine if I'm in a locally flat space, right? But I know that this combination right here doesn't behave like doesn't have good tensorial properties. It doesn't transfer properly. But hey, If this is true in my little area here that's flat, what must be true in general? I can replace this guy here with a covariant derivative. So what I could say is that this guy really, when that's always going to transform properly, is going to be this guy here. This is just a special case of this, because again, if I'm in the locally flat space, I get this. If it's true in the locally flat space, then it has to be true in the general case. That makes sense? Now, what I want to convince you of is that if this V nu here, if it's just our form velocity, the dx nu d tau, that's nothing but the geodesic equation. So let V nu be equal to, be defined as just our form velocity. Let's see what we get. So in this case here, we get this. Yeah, I put this guy first. Is this coming in?
Where did that come from?
I just put that in here.
Uh. Where does the T come from? Or is it supposed to be?
Oh, that's the tau. Oh, yeah, I need one more thing here. I can patch up there, so I won't go back. We're good. We're fine. This guy here is what? Who's this guy here? Okay. And then we have this guy. Now, I want to go back here and I kind of want to look at this guy here. What does it mean to parallel transport some quantity? We've looked at this before. What it really means is that when you move these components, you know, along some path here, the components don't change, right? So what we expect here is that naive, it basically means that the components of the parallel transported vector don't change. Okay, I'll set this up and then I can't finish that. I don't want to push it. It's not hard, but it's not obvious. The components of the parallel transported vector don't change. Okay, so what we expect here is that basically if you were to take this quantity here, okay, and you're going to move it along some basically geodesic here, or some path here, you'd expect this to be 0. Because you're going to expect those components to change if you're parallel transferring this. But what I want to convince you of is that when we do that, that's going to be the geodesic equation. We're going to recover the geodesic equation. Okay. And I can't go through all that without it being rushed and just being much more, so we'll pick this up here on Friday, pretty much on Tuesday. Turns out that Tuesday follows Monday. It's Friday does too, but there's an extension of basically 3 days between. Therefore, it'll be Tuesday, maybe tomorrow. Good to know. And it's gonna be actually, it's not that hard to see. You know, you're gonna put in for this guy here, so you're starting to see the gamma phone, you're starting to see the chrysalis and you're gonna get these two guys here, so it's already starting to look like the chrysalis. Well, it's starting to look like the legit SE version. Okay. Okay. Then we have to do some analysis, so. Okay, we're done for today. Leave that class, right? That's fine.
Why is that a bad thing?
Oh, no, it's a good thing that's your class. That's